Today we're going to continue talking about linear ODEs. In particular, we're going to have a look at linear ODEs as they occur in initial value problems, and we're going to have a look at a mixing problem, the problem of mixing two chemical solutions together. So as usual, when we're given an initial value problem, the first thing that we do is we solve the ODE, and then we find the values of whatever unknown coefficients are in the problem using the initial condition. So let's go ahead and let's try that here. Let's solve the initial value problem where we have x times y prime minus y is equal to 2x squared with the initial condition that y of 5 is equal to 1. Now the first thing that we need to do is get this linear equation into our standard form. So I'm going to divide everything by x. And now I'm going to calculate our integrating factor, e to the integral of negative 1 over x dx. And the simplest possible antiderivative would be negative natural log of x. This can be simplified if I move that minus sign out of the way to just x to the minus 1, since the e and the natural log will cancel. So the integrating factor in my problem is 1 over x. Therefore, my solution y satisfies the equation 1 over x times y is equal to the integral of 1 over x times the function f of x given on the right side. The right side of our simplified equation. So in this case, it would be 2 times x. So that can be simplified pretty dramatically, and I have 1 over x times y equals 2x plus c, which after multiplying both sides by x implies that y is equal to 2x squared plus c times x. So now let's use the initial condition that if x is equal to 5, then y is equal to 1. Setting y equal to 1 and x equal to 5, I get 1 is equal to 50 plus 5c. So negative 49 divided by 5 is our c value, and therefore the specific solution to our initial value problem is given by 2x squared minus 49 over 5 times x. So nothing new there really. An initial value problem containing a linear ODE. Just solve the linear ODE using integrating factors and then find the value of the unknown coefficient. Yesterday we noted that one of the situations that can be represented by a linear differential equation is the situation of Newton's law of cooling. So recall that if we had an object with temperature capital T left in an environment with an ambient temperature which is traditionally denoted by T sub ENV for the temperature of the environment, then the differential equation that corresponds to that is the derivative of T with respect to time is equal to some constant K times the difference between the temperature of the object and the temperature of its environment. So if we denote the object's initial temperature by T sub 0, let's see if we can find a general formula for the temperature of the object at any given time. Now the first thing that I'm going to do is I'm going to rewrite this in standard form. The derivative of T minus K times T is equal to negative K times the temperature of the environment. So in this case, our integrating factor, which I will call u of lowercase t, because our independent variable is implied to be time, will be equal to the integral of e to the integral of negative k with respect to t, which is e to the negative kt. So that means that our solution, our capital T in this case, satisfies the equation that u times capital T is equal to the integral of u times this function on the right side, which in this case consists of just the two constants, negative k and the temperature of the environment. So let's go ahead and finish this integral. We have e to the negative k times lowercase t multiplied by capital T. Now this negative k t of the environment, that's all just constants. Really, my attention is on this exponential term. And so if I integrate that, I get a negative 1 over k from chain rule times negative k temperature of the environment. And of course that negative k and this negative k cancel out. Then we have our infamous plus c. So finally, to solve for the temperature at any given time, what do we get? When we divide both sides by e to the negative kt, we get the temperature of the environment plus a constant c, e to the now positive kt. So now that we've found a formula for the general solution to the differential equation, T prime equals k times T minus T of the environment, let's go ahead and see what happens if we set T of 0 equal to this value T naught. So if I plug in T equals 0, then the exponential factor becomes 1, and I'm left with T0 equals T of the environment plus C. And therefore, if I take the initial temperature and subtract the temperature of the environment, that's going to be equal to my C value. Therefore, our temperature at any given time is equal to the temperature of the environment plus T0 minus temperature of the environment, e to the kt. Now that was a lot of labor up front, but now let's see if we can exploit some of that to answer a specific question. For example, what if the initial temperature was 0, the temperature of the environment was 25, and the heat transfer rate was given by k equals negative 0.2. What formula could we use to give the temperature of the object in this case? Well, now that we have done the work to find a general solution to a heating-cooling problem, all that we have to do is plug this information into that general formula. So the temperature of the environment is 25. The initial temperature of the object is 0. So 0 minus 25 is negative 25. And we were told that the value of k is going to be equal to negative 0.2, and that will be multiplied by T. So we did the labor up front, but now we can use this general formula in basically any heating/cooling problem. All you have to do is fill in the blanks. To conclude, this is going to be the question that is emblematic of differential equations as a class, the mixing problem. So, we've got a tank into which two chemical solutions are being poured. Then the two solutions are being mixed in the tank and the mixture is being poured out. Now, pure water is coming in at a rate of 1 liter per second. Salt water is coming in at a rate of 2 liters per second. And we're told that the concentration of the salt water is 10 grams of salt per liter. I have no idea if these numbers are realistic, but they're nice round numbers, which is good enough for me right now. Now, these two substances are being mixed in a tank, and then the mixture is being poured out at a rate of 2 liters per second. So let's see if we can figure out a function that will tell us the number of grams of salt in the tank after t seconds. So in order to do that, what I'm going to try and do is set up a differential equation for the number of grams of salt in the tank. I'm going to try and set up an equation in terms of the rate of change of the number of grams of salt in the tank. Now the salt is changing as a result of two things: the salt which is coming in and the salt which is leaving. If I can figure out how much salt is coming in versus how much salt is going out of the tank, then I will be able to set up and solve a differential equations problem to find the function s. Okay, now the easier one here is salt in. Salt water is coming in, and that liquid is coming in at a rate of 2 liters per second. The concentration of salt in that water is given by 10 grams per liter. So if I do a unit analysis and multiply those two quantities together, 20 grams of salt per second. So to summarize what I did just there, to find the grams of salt that were coming into the tank, I took the flow rate of salt water and then I multiplied it by the concentration of salt water. Of course, the pure water in this case is not contributing any salt entering the tank. Now to find the salt out, I'm going to need to do something similar. I'm going to need to take the rate at which the mixture is leaving the tank, in this case 2, and multiply it by the concentration of the mixture. But the question is, what expression can I write to represent the concentration of the mixture that is being dumped out of the tank? Alright guys, I decided to make a few small changes to simplify the problem a bit. We will get back to the more complicated version of this problem, video 15 or 16 or something like that. But I did make one small change in order to make this problem easier for right now. I have decided to make it so that the amount of fluid that leaves the tank is equal to the amount of fluid that enters the tank. So that way the amount of fluid in the tank does not change over time. And I've gone ahead and added the assumption that the tank begins with 10 liters of water, and so the tank will always have 10 liters of water. I've done that for simplicity's sake. Okay, with that retcon in there, with that correction, let's go ahead and let's try and find an expression which represents the concentration of the mixture which is coming out of the tank. Now, the concentration of a substance is equal to the amount of that substance divided by the amount of liquid that it's dissolved in. So the concentration would be equal to the grams of salt in tank divided by the amount of liquid in tank. Now the number of grams of salt that's actually in the tank is the quantity that's being represented by the letter capital S. The amount of liquid in the tank, as a result of the correction that I made, starts out at 10 liters and remains at 10 liters throughout all time. So the amount of liquid in the tank is constant at 10. So this would be the concentration of the mixture coming out of the tank. And if I put that back into the equation above, then I would have that the rate of change of salt over time is equal to 20 grams of salt per second minus 2 times S over 10 grams of salt per second. So we've finished setting up a differential equation which tells us how the salt in the tank is changing over time. Now, in order to find the function S, all that we need to do is solve this equation using, for example, integrating factors. So, setup is all done. I've gone ahead and simplified our equation. I've removed all those pesky units that physicists and engineers love so much. I've done some simplification, and then we have the equation here. That S prime is equal to 20 minus 1/5 times S. Let's go ahead and rewrite this into standard form. And let's find our integrating factor. U of t is equal to e to the integral of 1/5 with respect to t. Which means that our solution, in this case S of t, the amount of salt in the tank at time t, multiplied by e to the t over 5, is equal to our integrating factor multiplied by the function 20 on the far right side of the simplified differential equation. So if I integrate that, I get 100 e to the t over 5 plus c, and after dividing both sides by e to the t over 5, this implies that the grams of salt in the tank after t seconds is equal to 100 plus c e to the negative t over 5. So what data can we use to fill in the value of c? We need an initial value, and that initial value is given by the sentence underlined in pink right here. Initially, the tank contains 10 liters of pure water. And as a result, initially, the tank does not contain any salt at all. As a consequence, if I plug in t equals 0, then the output will have to be 0, which forces c to be negative 100. As a result, what function gives us the number of grams of salt in the tank after t seconds? The function is 100 minus 100 e to the negative t over 5. So this is an introductory mixing problem. We will return to problems of this nature later on, but I did want you to see an example of how linear equations can be used to tackle real-life applications such as this one. This concludes today's material. We practiced solving more linear ODEs, in particular in initial value problems. We found a general solution to the differential equation corresponding to heating and cooling, and we found a solution to a differential equation corresponding to the mixture of two solutions.